Broadcasting around the world. This is Engineering Tomorrow, the podcast committed to bringing you the best in commercial construction, design, and engineering from the brightest minds in the industry. This is the stuff they don't teach you in school. So sit back, relax, and open your mind. You're about to get the insider knowledge to improve your next construction project or advance your career. This is Engineering Tomorrow.
We are back from our winter hiatus and break. I am your usual host, Brian Gomski, and we have a couple of very prestigious and important guests on the show today.
Where?
I've heard amongst circles. We've got a couple of new things going on this year. For those of you listening on Spotify or iTunes or any of your audio podcasts, we're incorporating video this year. So we are going to be posting links to that in the show notes. And feel free to also find us on Engineering Tomorrow on YouTube and subscribe to the video podcast there as well. So jumping into our very first topic of 2022 is cooling towers. Counterflow versus Crossflow. And we've got a lot of requests for this topic. So I wanted to find the two best people on the planet that can speak to this. And we have Troy Gladstone and Ryan Miller.
You could not find those people. So
I could not find those people.
Yeah.
So I woke up Troy and Ryan from their naps. No, but seriously, you guys have been in the industry for a long, long time. No cooling towers in your sleep. So let's just quickly, if you guys can introduce each other and just give a quick background on why and how you know cooling towers.
Go ahead, Ryan.
Yeah, you bet. Honored to be here, Brian. This is fun. I'm flattered at the introduction. Fantastic. Love it. So, yeah, I started into the world of cooling towers about 12 years ago and entered into the Marley world in the field erected side. So learned a lot about those gigantic towers that you see at power plants and refineries and things like that. And then quickly made my way into more of the commercial HVAC side. So I've been dealing with package cooling towers for, I guess, about 6 years at Marley and then about 3 years here at Midwest Machinery. So I've seen the inside of how the manufacturing community works. And then I've also seen a lot of the actual field application of the various types of cooling towers. And I'll tell you one really nice thing about working for Marley and then for a representative firm that represents Marley is that because Marley has all the different types of cooling towers, there's no need to try and put a round peg in a square hole. We are able to really be consultative and figure out what works best for each individual application. So it gives a lot of freedom and a lot of confidence in being able to make sure it's the right solution.
Cool.
Troy?
Thank you. I'm Troy Gladstone, president of the Midwest Group, and the Midwest Group is a holding of companies, which is Midwest Machinery, our original St. Louis office, Midwest Kansas City, Midwest Machinery Oklahoma, and then we also are a partner in Engineered Products in Denver, Colorado. And I guess I don't know if this is a brag or an embarrassment, but I've been associated with cooling towers for 36 years now, going back to when I was 14, mowing the lawn at the office and working out in the shop. And when I was 16, I started rebuilding gear reducers, which we'll talk about a little bit, which is a major component within the cooling tower. So I did that through high school and college, and out of college, thrust into sales engineering. And I don't know, about 10 years ago, we were able to purchase the company. And so it's 36 years of somehow, some way affiliated with cooling towers, and remarkably, I still learn things today. So yeah, happy to be here. I think this is fun. I like the video content, with the exception of just seeing me on the video, because I'm reminded how old I am. But I think it'll be good for the video because it's a technical podcast. And so there is technical materials and presentations that we're making, and it'll be helpful for those that are listening and watching to see what we're talking about.
Yep. So we are going to put some visuals on this video feed, and we will absolutely do our best to describe what you're seeing for those. I know a lot of people listen in their cars or maybe on the job sites or whatnot. So we'll describe it, but when you do have time, definitely feel free to check out the video feed. So without further ado, let us get into.
You're not supposed to say that. That's like the most trite thing in broadcasting.
What do people say now?
I don't know, but I know you're not supposed to say that. So
let's roll.
All right, cool. I like it.
All right, so we've got this new software. We're going to pull up the awesome screen here.
So Ryan, you mentioned, or Brian, I don't remember who did, but this is a often requested topic and presentation, and I would agree. It's probably this is a podcast, so it's more of a conversation, but we're using pieces of PowerPoint presentation that we do all the time for lunch and learns, and the conversation is Counterflow versus Crossflow, but the feedback we've always gotten is that it's a good topic because it helps people really understand the components of a cooling tower, the different types of a cooling tower, and most importantly, what are the right applications for different types of technology. And Brian, as you said, Marley's patented. Actually, Marley has I know Marley has the most patents in the cooling tower industry.
That's right.
They have for sure patented every type of cooling tower that you can imagine. Great ideas and horrible ideas. I mean, there are cooling towers that we no longer use because they seemed like a good idea on a drafting table, but in practical application, they were miserable failures. So the point is that today we do have the luxury of always being able to recommend the right type of equipment for the application. So yeah, we're never making a recommendation because it's what we have. It's because it's what we think is.
Right. And Troy, I think you make a great point about some of the failures too, right? Like we all know that you learn best sometimes from when you fail, and Marley has failed in both overall towers that they produced and even on the component level. I mean, even looking at some of the water distribution nozzles that they came up with over the course of time, I mean, just disastrous, but it helped them learn what didn't work and hone in on what really does work. And
I mean, you think about it, we've tried plastic cooling towers, and those, we're not even allowed to talk about those anymore because there's some flammable issues with them. Fiberglass towers, they have a place, but sometimes fiberglass, especially in seismic considerations, can be a problem. Yes, we are a sales organization, so we do have a brand that we like and we prefer, and we're going to do our best not to make this a conversation. And it's probably notable to say that there's really three major manufacturers in this space: Marley, BAC, and Avapco. It's no surprise. And I think the good news is they're good competitors, and the types of towers that we're talking about here, Counterflows and Crossflows, all three of those major manufacturers offer those. So anyway,
yep.
Let's get to it. And Ryan, I guess you're the technical expert, and I'm the color commentator, and that makes you the producer, Brian.
I'm the host that everyone knows and loves. Yes.
Okay.
Ryan, real quick for our maybe college listeners or engineers, brand new, in 30 seconds, what is a cooling tower? What are we connecting it to?
So a cooling tower is heat rejection equipment. So it's taking heat that's been pulled out of a building through various means and sending it out into the environment. It does so in the most naturally efficient way humanly possible, and that is by putting air and water in direct contact with each other. So many heat exchangers that you think about have some kind of a medium, like a radiator that has tubes, right? That you're transferring the heat through those tubes from the fluid to the air. In this case, we're putting the air and water in direct contact with each other. And by doing that, we're evaporating a certain amount of the water. And when it makes that phase change from liquid to gas, it releases a tremendous amount of energy. It's 1,000 BTUs per pound per hour of water. So it's far more than anything else that can be done with any kind of heat transfer. And so, yeah, it's the most efficient way to get heat.
Yeah, I mean, it's a good point. You compare that to in a typical large commercial building or hospital or school, we're usually using a chiller to cool water down to 44, 45 degrees. And then next stage in that cooling process would be a cooling tower. But they're both doing essentially the same amount of cooling. There's even an argument to be made that the cooling tower is actually cooling a roughly 20% greater tonnage of load for the cooling or for the building itself, but it's literally using a fraction of the horsepower that it's the chiller that it's serving is using to move the same amount of heat. So nature works in our benefit for sure.
Yeah.
Okay, so now we've got we know what a tower is. Now we've got a couple different types of towers we're going to talk about.
Yes.
Go ahead.
So let me, I guess, just start with, there's, again, Marley does all the different types of towers. And just real quick, the way those can kind of be segmented, I guess, or delineated is I mentioned the field erected versus the factory assembled. Field erected is giant football field sized towers where you send a construction crew out to go build them. Factory assembled is we build them in a factory, put them on a truck, they show up on site, you set them in place, pipe them up, wire them, and they're off and running. So today we're going to be focused on those factory assembled products that have their application primarily in HVAC. Just as a side note, in addition to the Crossflow versus Counterflow that we're talking about, there's also induced draft towers versus forced draft, where you're pulling air out through the tower, creating a vacuum, versus pushing air, creating a positive pressure environment inside the tower. And then there's also open cooling towers where the process fluid or the fluid that's coming from the chiller, for example, is put in direct contact with the air. And then there's also closed loop fluid coolers where we're still using evaporation because we have water that recirculates within the tower itself and interacts air to water. But then it also has another step where the process fluid is kept separate through coils. So those are kind of the I guess, four ways you can delineate: FEP, FAP, counter versus cross, force versus induced, and open versus closed circuit. Again, today we're going to be focused primarily on the Crossflow versus Counterflow.
Awesome.
Hey, Ryan, why do we call them Crossflow and why do we call it Counterflow?
Yeah, it's kind of an amazing story, Troy. The story goes, and I don't know for sure if this is true, but when they were first coming up with the different styles of cooling towers, they got a host, a dozen rocket scientists and put them in a room for a week to come up with the best names for the different types of towers. And what they came up with was for the towers where the air moves across the water, they call it a crossflow. It's amazing. For the towers where the water and the air flow counter to each other, they call it a counterflow. So, genius.
Yeah, wow. Rocket scientists. A little engineering humor there, everybody.
Yeah. I might have to add a laugh track to that one.
Yeah, please do. So anyway, that's really the point. Is on a Crossflow tower, we are pulling air in horizontal while the water comes down vertically, and then after those two have interacted, then we're turning the air out and pulling it out of the top of the tower.
Right. If you're looking at the visual, you can see a Crossflow tower on the left of the screen. And just like he says, it's coming in, turning 90 degrees, going out the top. The counterflow tower is also interesting because it has air inlet on 4 sides. And these two towers right here are, I would say, 95% of what's installed in commercial and light industrial applications for cooling towers. So this is almost what we do exclusively on a daily basis.
For sure. Yep. And I'll also note that the main componentry in cooling towers, it consists of a way to move air. So we have a fan, typically with either a gearbox or a belt, and a motor, so your mechanical equipment. We have a way to distribute water over the heat transfer media, and then we have the heat transfer media. In addition to that, we have places to collect the water, and then just a housing to kind of contain it all. So both the Crossflow and Counterflow can have all of those different components, but they certainly interact in a little bit different ways, which creates advantages and disadvantages depending on the situation.
So as we go through the comparison of the two, we're going to talk about a handful of features, or I don't even know features, but a handful of things with each of them, and compare and contrast them, and then we'll give a nod as to what might be, who has an advantage in a certain characteristic. So I think you can go with this first one right here.
Sure. So the inherently, with just the way that these things are designed, the Crossflow tower ends up with a very large plenum area. So this is the area between where it has the air, where the air has left the heat transfer media, and before it exits the tower through the fan. This large, as we're using this plenum area to turn the air 90 degrees, creates a space that allows for easy access inside the tower. So a person can stand inside this area and have plenty of room to move about.
Which I think we're going to be talking about maintenance in a few slides, and so we might even need to bounce back to this to show that.
Yeah. So that is where that kind of comes into play. On a counterflow tower, because we're bringing air into the tower horizontally, and then we turn it 90 degrees before it interacts with the fill media and the water, we have to have a plenum area at the bottom of the tower. It's much smaller, a few feet tall, and takes up the whole footprint of the tower. And then we also have to have a place where, after the air has moved through the water and the heat transfer media, and to kind of collect the air and move it up out of the tower again. So we have another plenum area that's towards the top of the tower. And this is, again, where the mechanical equipment resides. And this is, again, a much smaller area than what you would find on the Crossflow tower. So on a Crossflow, you have one large plenum. On a Counterflow, you have two small plenums. So, yeah. Okay. Well, one of the first things to consider is tower space requirements. And we'll get into a number of aspects of this. But to start with, what you'll notice, if you're seeing the visuals, or if not, we'll describe it with the Crossflow tower having two air inlets. You'll have two sides that are air inlets and two sides that are casing, kind of boxing it in. So that ends up kind of naturally creating a rectangular footprint shape. On the Counterflow tower, because we're bringing it in all 4 sides, before we turn it up, all sides are kind of equal. So we end up with more of a square shape. And what you'll find is there's kind of a paradigm shift depending on the tonnage that you're looking at. Anything below roughly 750 tons, you're going to probably have a little bit larger footprint for the Crossflow tower. And that, again, is because it's rectangular. We have that large plenum area that we talked about, kind of spreads the tower out horizontally and gives a slightly bigger and more rectangular footprint. Counterflow, again, below 750 tons, it's a smaller square footprint. Now, with the Crossflow tower, when we get above 750 tons, we have the ability to have a double stacked tower. Essentially, we have a bottom tower that consists of your cold water collection basin and half of your fill material. And then you have a top module that sits on top of it that has more fill material, and then all of your mechanical equipment and your water distribution system. So what that does is it allows us to have, as much as twice as much capacity in the exact same footprint. Now you're twice as tall, but you're staying in that footprint. The Counterflow tower, we can't stack it up. It's already stacked up. So it's kind of how it's built.
Yeah,
so
by nature, it's a taller,
right,
taller type of cooling tower. Which, when you think about installing these, it's pretty rare. Right here, we're looking at a single cell tower. And as the size of the project dictates, we add cells to it. So you might stack 3 of these side by side, interconnect them with, equalizers or flumes. And it's kind of important to note that we would call, for example, if we saw 3 of these stacked together, we would call that a 3-cell tower rather than 3 towers. I've had some problems on submittals before with confusion on that. It could actually create some massive expensive problems if you don't have that nomenclature right. But, so just looking at a single cell tower, the NC Crossflow tower looks like it takes up a lot more space, which probably in a single cell configuration, it does take up more space. Whereas the Counterflow tower is square. And I think the next slide, if you want to go to it, actually,
sure.
The next slide is talks about height. So the Counterflow tower is by nature taller, but when you start stacking these up, that Counterflow tower only has air inlet on 2 sides. So the inherent advantage of a footprint on a Counterflow tower with a single cell kind of goes away when you put multiple cells together and your installation gets longer. So really, if we're talking about, who's got the advantage of space, I think I would probably have to say the Counterflow probably is a more compact, at least in a single cell configuration. Would you agree, Brian?
Yeah, for sure. Just looking at the space that the tower takes up itself for this equal capacity, you're going to have a less square footage and a smaller tower. Now, in just a minute here, we'll talk about another aspect that's important, and that's how we leave space to get air into the tower. So that's a little bit different way to look at it, but
yeah,
talk about that too. Before we get to that, though, since we're on the height discussion, that plays into the pump head to be able to get water into the cooling towers.
Yeah, this is super important. I think we should spend a little time on this.
It's a little and probably a little bit counterintuitive if you don't know a whole lot about cooling towers. So on a Crossflow tower, we have a gravity fed basin that's at the very top of the tower. So if you're looking at pump head and you're looking at your static lift, we have to be able to get water all the way to the top of the tower. Now, again, the Crossflow is typically a little bit shorter than the Counterflow, but still, we got to get it all the way up. On the Counterflow tower, we only have to get water, I don't know, maybe 2/3 of the way up. So the static lift is going to be a little bit less. But the rest of the story, for the Crossflow tower, when you get the water up to the top and you put it into the gravity fed basin, it's just flowing into there's no back pressure. It's just flowing into a panned basin. So the pressure you get up to the top is all the pressure you need, and then you're done. On the Counterflow tower, we have to pressurize the spray system. And the reason for that is, I don't know, Troy, can you guess why we would have to have a pressurized spray system? Why can't we just put a gravity-fed basin in a Counterflow tower?
Well, thanks for asking, Ryan. The hot water basins in a Crossflow tower, they have a bunch of nozzles, as you can see from that visual. And those nozzles have orifices that are sized to maintain roughly 3 to 5 inches of head above them. And so it's a tightly engineered criteria that says 3 to 5 inches of head at a certain flow rate will give a spray pattern that completely covers that fill area. But the challenge with a counterflow tower, where we have a pressurized spray system, we have to have a pressurized spray system because that air has to pass through the distribution system.
Yep.
Yay, I passed the test.
Yes, you did. I've had that question. They're like, why don't you just, why do you have to have this extra head pressure inside the counterflow tower? Why don't you just use a gravity-fed basin?
Yeah, well, because the water distribution system is in the airflow as opposed to the Crossflow tower where it isn't. And so we can't, we have to have pressure to be able to get a spray pattern across the fill, which then adds, honestly, a considerable amount of pump head. And this is almost never thought about when engineers or design build contractors are laying out a job and really comparing the actual required pump head to get it into a Crossflow tower versus a counterflow tower. And I mean, you can see right there in this visual, we're saying on, 750 ton cooling tower, we need about 13 feet ahead to get it, from basically the top of steel into the cooling tower, whereas its equivalent counterflow tower is going to require sometimes 25, almost 30 feet of head. And so there's a good 10, 15 feet of additional head required. And if you think about, a good size installation that might be 750 tons, you're talking close to 2,500 GPM or 2,250 GPM. Those are big pumps, so you might have 7,500 horsepower pumps, each required to do another 10, 15 feet ahead. That's going to be massive energy costs going forward. Yeah. So for that reason, I would say the Crossflow tower has a very significant advantage with the distribution system and the fact that we save a ton of energy as compared to the counterflow tower. And we'll talk a little bit about it too, but owners that have counterflow towers, and we're talking, facility type owners, institutional type owners where they have robust maintenance staff, they're not a fan of the counterflow tower because those spray systems do require maintenance. Actually, any spray system requires some maintenance, whether it be the Crossflow or the counterflow. And I know I'm probably stealing some thunder coming up in a little bit, but if you're looking at this visual, you've got a pressurized spray system. What happens when you get leaves or debris or plastic bags, things that are, in the airstream that this tower, cooling towers are great air filters. Not to mention pipe scale, all kinds of things can clog the nozzles. And so if you clog the nozzle in a counterflow tower, just looking at that picture, how are you going to get to that? And how are you going to find out what nozzle's clogged? Compared to the Crossflow tower that has a fan deck, handrails, safety ladder, all of that. And then, you pop off the basin cover and you can see, a couple hundred nozzles in front of you and see if there are any obstructions. So it's a huge maintenance saver and safety issues. So anyway, go ahead.
Definitely teased the big reveal there, Troy.
All right, sorry. Well, you stole my thunder earlier on something else, so touché.
Tend to do that. But no, this is a good time to discuss that portion of the maintenance as well. Operating weight. Sometimes this is a concern, sometimes it's not. If you're sitting on grade, clearly it doesn't typically matter. If you're on a roof and you're kind of on the cusp of weight limits, sometimes this can become important. The Crossflow tower, because it holds water in that gravity-fed basin, like Troy said, you're gonna have 3 to 5 inches of water depth for the head pressure on all of those little nozzles. That adds water's relatively heavy compared to the stuff that's in these towers. So you're going to have more water and thus more weight. Further, because the footprint's a little bigger in the smaller tonnages anyway. The cold water basin where we're collecting all the water at the bottom, it's going to be a little bit bigger because it's taking up the whole footprint. So we have more water at the top and more water at the bottom. So the Crossflow is going to be a little bit heavier. The Counterflow, like I said, we have a pressurized spray system. It's a pump head penalty, but on the flip side, you don't have as much water in the tower at any given time in those pipes that are distributing the water. And then again, like I said, the cold water basin is smaller. Now, one thing I will point out about a Crossflow tower is there is some flexibility in the operating level of the cold water basin, depending on what your flow rates are. If you're right on the cusp of being a little bit too heavy, you do potentially have the ability to lower the operating level in the cold water basin, and thereby take, even a couple inches takes quite a bit of weight out of there. So,
yeah. I think, so when I think about this, when does it really matter? A couple of places. And so I don't want to minimize the advantage that the Counterflow can have in weight. Sometimes you're replacing existing cooling towers. And, if you've got a service contractor replacing an existing Counterflow tower, and we blindly recommend a Crossflow tower in its place, that could create some problems because the Crossflow tower is likely going to be heavier. And if we're heavier, then that's going to push somebody into doing a review and an analysis on the existing structural steel. And that could be expensive, and you might find out that you can't support it. So, it's really important when you're looking at replacing an existing tower to try to replace it with something that's equal or less weight, because then in theory, the structural analysis has been done back when the tower was installed originally, and that what you're putting on is the same or less weight, and therefore you don't run into issues. The other thing I've run into is on when we're talking with contractors who are putting together plans and bids to replace a cooling tower, to install a cooling tower, the pieces, the crane hoist pieces on a Crossflow tower will be heavier than that of a Counterflow tower, of its equivalent Counterflow tower. So sometimes when you're looking at the crane hoist, you should pay attention to it. And usually it doesn't matter, but there can be situations where it puts you into the next size of crane for the project. So through this whole thing, you're probably going to hear a bias of ours, which is towards Crossflow towers. So I always have to remind myself where the Counterflows truly do have an advantage.
Yeah. Did we talk about the airflow space around a tower?
No, I pulled that slide out of this before we started.
Okay. All right. We'll skip that then.
We'll leave something for the next time.
There you go. Perfect. Okay. And so so we've touched on this aspect a little bit, maintenance considerations. There's quite a bit to talk about here, and the differences are pretty significant between the two towers. So as I mentioned in the opening, the Crossflow tower has a very large plenum area. Within that plenum, you're able to access the inside of the fill, where the drift eliminators, which are often part of the fill material itself. It's a
Ryan, if you move your cursor, will it show up on the screen, I think?
Can you see it? I'm moving it now.
No, doesn't work. Never mind.
Okay.
All right, first time.
It wouldn't help our listeners anyway.
Rookie move here.
Yeah, here.
Sorry.
So you stop.
Anyway, where were you? I interrupted you.
No, that's fine. I was just talking about the large plenum on the Crossflow tower, Troy.
Right.
And
okay.
So, like I said, it gives access to the inside of the fill. It gives good access to the cold water basin for inspection, cleaning, things like that need to be done. And when I say good access, I mean you're standing in there with plenty of room to move about, take tools in there, whatever you need. You have all the space. And then importantly, also, you can access all of the mechanical equipment, the motor, the gearbox, the fans, all of that can be easily gotten to within that plenum area. On the flip side, on a counterflow, the the underside of the fill in the cold water basin, you have to remove the louvers from the air inlet. They come in little slats, essentially. Pull them out, and it's 3 or 4 feet tall. You got to crawl in there to get anything done.
Yeah, you actually need tools to do that. Whereas the Crossflow tower has a handle and a large door that you can just walk into.
Yep. It actually, Troy, makes me think of I like analogies. And one analogy that always comes to mind when we're talking about this is, so in my residence here in the Kansas City area, I have a full basement. And so my mechanical equipment, my furnace and AC and all that sit in the basement, and a lot of the plumbing. I'm able to just walk down there and have easy access to it with just opening a door, walking in, and standing there. Bring my toolbox with me, whatever. I also happen to have a couple of rental properties in the Kansas City area, and they happen to be in areas where there are not basements. So instead, they have crawl spaces, and the mechanical equipment and plumbing is actually underneath the main floor in like a 3-foot crawl space. So in that case too, you have to take a hatch off, crawl underneath there. It's dirty. It's very uncomfortable. It's hard to work. Stuff gets neglected. You don't want to be in there. It's no fun. The counterflow tower, in my mind, is kind of similar in that I mentioned the cold water basin, getting into there, having to have tools to remove that quote unquote hatch.
And you're crawling in there. I mean, you can't. I mean, it is. Yeah, it's a wet mess. It's full of water. So there's really. The only time you could go in there is when the tower is shut off and almost drained, right? Right.
And that's another good point. You can go in the Crossflow tower while the water's still running.
Well, the tower's running. I mean, I've been in hundreds of cooling towers while it's operating.
Yeah.
I don't know. Probably shouldn't say that out of safety concerns, but a lot of times we have to diagnose problems and troubleshoot what might be causing issues, and so we want the tower to be running. We want water being pumped over it so that we can try to analyze where vibrations are coming from. You could never do that in a counterflow tower.
Right. And I think even worse than the cold water basin access on a counterflow tower is the upper plenum where the mechanical equipment is. And as you mentioned earlier, Troy, the spray distribution system, that's equally as tight, equally as hard to get into. It's up off the ground. In this case, you're crawling on top of very uncomfortable eliminators. You have to put plywood in there to make sure you don't damage them. Really difficult to access the mechanical equipment. And then even more difficult to access the water distribution system because you actually have to remove those eliminators that are packed in there pretty tight. It's not fun and it's not easy. You got to pull them out and then get down underneath there to be able to check nozzles, replace nozzles, things like that.
Right.
So,
yeah. So reality is on counterflow towers that might have clogged nozzles, they're going to be clogged for the rest of their life because nobody's going to go in there and actually do that.
And that's the point. So cooling towers kind of have a reputation for getting neglected anyway because they're on the roof or they're out back. They're not in the mechanical room. People forget about them. They don't want to go out on a really hot day to do what needs to be done, or even worse, on a really, really cold day to do what needs to be done.
Yeah.
But beyond that, on a counterflow tower, it's way more difficult to get to. And in a lot of cases, it's kind of out of sight, out of mind, which, I wouldn't want to call anybody to the carpet, but I've actually had maintenance folks say, well, I like this counterflow tower better because my boss can't see what's going on there. Crossflow tower, they can see their scale buildup on the fill that needs to be addressed, or they can poke their head inside the tower and see oil dripping from mechanical equipment, and it can be addressed immediately. On a counterflow tower, you just kind of forget about it, which is easy sometimes, but your equipment doesn't work very well and it doesn't last very long.
Yeah, they'll find out what's inside there on July 25th on a full design day. Yeah, when it's 82-degree wet bulb in Kansas or Missouri.
Right. So,
So
yeah,
clearly, well, actually, I want to make another point, and we're going to get to it in a minute in terms of installation requirements. Sometimes I'll hear complaints from installing contractors, and they'll say, "Dang, this Marley or this NC or this Crossflow tower, it just takes so many more man hours to install than a Counterflow tower." And that's usually true. And there's a big reason for that. If you think, for those who work with air handlers, in the air handler world, you have packaged air handlers, and then you have fully custom air handlers. And why do people use fully custom air handlers? Because they want a lot of access and maintenance and all kinds of features that make it a more complicated air handler. Well, the same is true of cooling towers, especially Crossflow cooling towers. Because our tower is so maintainable, the Crossflow specifically, we find that the end users that specify and purchase these do a really good job of maintaining it. So as they're gaining access to the plenum or to the fan deck or to the motor that sometimes hangs off the side of it, it becomes part of their PMs, and then they want safety while they're doing all that work. So we have many, many options to put access platforms on these, internal access platforms on some of the double-decker towers that you referenced earlier. We actually put a plenum walkway in there with a ladder that goes to an intermediate walkway that then folks can service the gear reducer and the motors with from the intermediate walkway. And all of that, well, a lot of that has to be field installed, because you just can't, even on this picture that we're looking at now, you can't ship that cooling tower with handrails installed on the top of it. And then you compare that to a Counterflow tower, which it's very difficult to maintain from the beginning. So what typically happens is the assumption is that we're not going to really do a good job of maintaining it, and it just doesn't, they don't get purchased and installed with as many accessories as the Crossflow tower does. So by nature, the Crossflow tower takes longer to install because you're installing stuff that the owner or the purchaser wanted, not just because it's a bigger pain in the butt.
Yeah. And I'll say, Troy, in fairly recent years, there have been some pretty big advancements made in the design of some of those railings and ladders and platforms as well. And they still take time to put on, and certainly more time than the nothing that goes on a Counterflow. It's a lot easier and a lot faster than it used to be to put some of that stuff on.
Oh, for sure. Yeah, you're right. It's a good point.
Yeah. Okay. Variable flow. So obviously, year after year, decade after decade, energy conservation becomes more and more of a topic. And so a lot of times we want to be able to, when we don't have load in a building, we maybe turn a chiller off or in some other way reduce the heat rejection that's coming out of the building. And therefore we can reduce the water flow, which is in a direct relation to the heat load that's coming out. So in a Crossflow tower, we have a really robust ability to do that. We can actually turn it down to almost 30% of design flow in a lot of cases with really no detrimental impact to performance or predictability of performance or consistency of performance. And the way we're able to do that is through that Crossflow, that gravity-fed basin. We can put dams, or in our case, we have what's called nozzle cups, and those are essentially just individualized dams for each nozzle. And what we can do is as we reduce flow, the water level in that hot water basin is going to start to come down, and as it does that, the pressure on the nozzles is going to go down, and you're not going to get good distribution. But if we block off some of the nozzles, then that we start to maintain that level and maintain that necessary head pressure over those nozzles to get good distribution. Depending on how much we want to turn the tower flow down, is the result of how many cups that we want to put in there. Now, these cups, as I said, they're like individualized dams. So when the water flow is full flow, that level is going to be above the top of those cups. And they're literally just cylinders. They're just cups. So the water will flow right into those cups and right down into the nozzle as if the cups weren't even there when we're at full flow. As soon as we start to turn it down, that water level drops. When it gets just below the tops of those cups, it maintains right there, so it keeps proper head on the remaining nozzles. And what we do is we start putting those cups on the plenum side, fan side, plenum side, towards the outside of the tower. So we always want our flow on the outside of the fill media, towards the where the air is coming into the tower. And there's a couple reasons for that. First of all, we want to maintain as much heat load as we can on that outside area of the fill that's interacting with the coldest air coming in. Because typically, again, this would be done usually in a winter environment or at a low load. So to mitigate against freezing, we want to keep full flow, full load on the outside of that fill, hitting that coldest air coming in. The second thing is, if you have kind of fill that's wet then dry, then wet then dry, you have more ability to build up scale over time. So we want to keep that as wetted as possible. If we had, let's say, water was just flowing through the middle of the fill, we'd be getting a little bit of splash out towards the outside, droplets here and there. In winter, those would freeze quickly. There's no heat load in those little drops. At other times, they're going to just evaporate there and leave scale on those portions of the fill. So by moving the water to the outside of the fill, keep the heat load there and we keep it wetted. And then you say, well, what about the fill that's behind it that doesn't have any water flowing down through it? That's going to get dry anyway, right? Well, no, because as we've said, the whole purpose of a cooling tower is to evaporate water into the air. So as the air comes across that water that's on the outside of the fill, it's going to pick up, it's going to get fully saturated. It's going to have plenty of water in it, and it's going to pull a little bit of that water with it, even in terms of droplets and stuff, and it's going to stay fully wetted as that air comes across the backside of the fill. So you mitigate against uneven flow, you mitigate against freezing, and you mitigate against scale. So that's on a crossflow. On a counterflow, there's really nothing we can do besides when we just turn down the flow, our pressure is going to reduce, and then those pipes that require pressure to pressurize those nozzles, once you get below typically about 70% of design flow, you're going to start not having good distribution. What happens when you don't have good distribution? You're going to have areas of the fill that are completely dry and other areas that are completely wet. And as air comes into the tower, it's going to choose the path of least resistance. And so it's going to go through the dry portions of the fill and not interact as it should with the water. And so you're going to get inefficient and inconsistent cooling. You're also going to get, again, the potential for freezing in those areas in the winter, and you're going to get scale buildup.
So when we talk about inefficient or inconsistent cooling, how does that manifest itself to the utility bill? Well, it's because, towers are wetted surface and air movement. So if we have less wetted surface, we need more air movement. So what will actually happen is we're going to have to run our fan harder at low flow on a counterflow tower than we would on its respective crossflow tower. And it's a huge difference. I mean, we're way in the weeds here on cooling tower design when we talk about variable flow nozzles, but it's worthy, in my opinion, it's worthy of getting into the weeds because, like you said before, well, 15 years ago, we'd always recommend don't vary your condenser water pumps at all. But today, as our control systems and we're all offering these central plant controllers now, as they've become more sophisticated, we know that we can effectively vary the speed of our condenser water pumps and the fan at the same time and have pretty significant energy savings. So it actually becomes pretty important to pick a tower when you're in those situations that has high turn down capacity, and it's more than, just as you described, it's more than the turn down capacity, because you'll see people advertise that you can turn this down to 30%, but it's how is it doing from 30 to 100% in terms of the efficiency it uses, or the brake horsepower it's using on those fans. It can be a significant difference. Crossflow versus Counterflow. So for that reason, we're going to give the huge advantage to Crossflow. Yes.
Yep. Crossflow gets the nod on variable flow.
Cool. For sure. How are we doing on time, Brian?
We're approaching Joe Rogan time frame, but
so 2.5 hours in right now.
Yeah, I mean,
but this content,
you know what?
So it's fire.
It is absolute fire.
Yeah.
And yeah. People will come back to it.
I was telling my daughter last night that she's in volleyball, and I was like, "Your serves are on fire." She's like, "Dad, it's not on fire. It's fire.
It's just fire."
And we had like a 5-minute conversation, and I couldn't understand it. And she finally just said, "Just accept it. Don't say on in front of fire," because that's how the kids do it. So anyway, did you know that, Ryan?
I did not.
There you go. If you want to be cool, just say fire.
We'll, on fire. Next episode, we'll talk about cap, no cap also.
Cool. All right, now I have to know. What is cap, no cap?
Lying or not lying?
Cap is lie.
Yeah.
No cap is not lying.
Yeah.
Yeah, I've tried to research the origin of it, and it's kind of still, there's not really a definitive answer, but
my mind is blown. I mean, so I'm the oldest person on this podcast, and I was pretty excited that I knew what fire was.
No, it's impressive.
Yeah, go on. Let's move on.
Okay. Okay, just real quick on recirculation. This is something that can certainly impact the performance of a cooling tower. It needs to be thought about when siting the tower, when deciding where to put it, how to position it, and of course, which type of tower you should go with if there's a risk of recirculation. So there's a couple things about a Crossflow tower that tend to give it an advantage for recirculation. First of all, it has higher outlet velocities. So as we're pulling air up out of the tower, the velocity of the air coming out is fast enough that it's going to get that air, that hot, moist air out up above the tower and away. So there's less risk of it being sucked back in. And of course, we're pulling heat out of water by evaporating it and warming that heat up. If the air that's coming in is already moist and already warm, it's not going to be as effective at evaporating that warm water that's coming down. So we want to avoid recirculation. I guess I maybe should have started with that. And so then the other thing about a Crossflow tower is because the surface area of the air inlets is fairly large, it's the whole width and the whole height of the tower, the air inlet velocities coming into the tower are much lower. So it's less likely to try and suck air that's above it down in there that's coming out of the tower. And then probably the biggest advantage is because there's only 2 air inlets, that means you have 2 case faces. And when you have the prevailing winds in any area are part of the equation for recirculation. So if the prevailing winds are coming across the tower, it may tend to catch that hot, moist air and try and pull it back down. But if you site the tower such that a case face is perpendicular to that prevailing wind, any of that hot, moist air that the prevailing wind does try to take with it and pull it back down is just going to hit a case face instead of hitting an air inlet face to come back into the tower. So the one advantage that a counterflow tower has is that, because it's taller at those lower capacities, there's a greater vertical spacing or distance between where the air is coming out of the tower versus where it's going back into the tower. So that just that space alone helps to mitigate somewhat against that recirculation. But you don't have, since it has air inlets on all four sides, you don't have the ability to turn it to be perpendicular to the prevailing winds. And so there's less flexibility in how you site the tower.
Which could all change as you make it a multi-cell cooling tower, and then you just have two air inlet faces on a counterflow tower.
True.
I have 2 questions. Well, one is, so this is saying that higher air outlet velocity and lower air outlet velocity is a plus. Can you elaborate on that?
I can't. I'm pretty sure that was an error. I don't, Troy, I don't know, maybe you know, but to me, having a lower air outlet velocity is a negative, as it has the
so you're saying on the counterflow. Yeah, this is so embarrassing. On the counterflow tower, it has a plus for lower air outlet velocity.
Should be a minus.
Should be a minus.
Yeah, but thank you very much for pointing that out, Brian.
Yeah, just in case someone was thinking that.
On a podcast, nonetheless.
Yeah,
millions and millions
of listeners. Hey, we're humans here.
Yeah. Hey, but maybe this is a teaser for a future podcast on recirculation, and you said the siting, the application of cooling towers in the real world, because I think actually that would be a really good one for us to do, because so many times our cooling towers are put next to a building or behind a screen wall, and that's where you can get into some real nightmares on recirculation and basically just kill the performance of your cooling tower. We've seen buildings that are short on capacity because people didn't pay attention to that.
Yeah.
So,
teaser for the future.
The other question I had is, in the winter, you can get a plume, basically a cloud coming out of your tower. If you're near an airport or someplace that could be a negative effect, would a counterflow or a crossflow does better with that at all?
So I think the slide that we're showing here would say we should give the nod to the Crossflow tower for recirculation. I don't feel strongly, maybe a 60% nod versus 40% for the counterflow, because I don't know, Ryan, do you think that I don't think there's a significant difference between the air outlet velocity, and the air outlet velocity is going to be what dictates how that plume gets away from the cooling tower. You're not going to be able to, there's mechanical ways that we can reduce the amount of visible plume on the cooling tower, which that's a 2-hour podcast in itself. Because basically what we do is we put a heat exchanger in the exiting airstream so that we condense some of that fog or that steam or moisture. And they work, they're remarkable and very, very expensive. So we like to sell them, and they solve a great problem. But personally, actually, to be truthful, we probably, I don't speak out of turn, but we probably have put more of those on counterflow towers than we have crossflow towers, the plume abatement solutions.
On the field erected.
Yeah, on the big towers. On the smaller towers.
It's the Crossflow tower is the model that has the coil application for.
Right. So I couldn't say that there's necessarily an advantage to reducing the visible plume. Would you, Ryan?
No, I can't think of why one would be better than the other. I mean, to your point, Troy, if it's a critical application, like Brian mentioned, an airport, for example, you really have to just go with, you got to bite the bullet and spend the money on full plume abatement.
Yep.
So.
Yeah. And then, in terms of recirculation, I think you should work with your Midwest machinery sales engineer on that, because the way we install it is much more important than whether we use a counterflow or crossflow.
Agreed.
So, I don't know. I would give this a neutral. What do you think?
51-49. How about that?
All right, fine. Your confirmation bias is showing.
So drift I guess the first thing I always like to talk about with drift is just to kind of clarify what it is and what it isn't. So I've had conversation with folks before who were concerned about drift in terms of water loss, water usage. And it's really, so with the cooling tower, as we said, the whole purpose and intent is to evaporate water. So on purpose, we're evaporating roughly 1% of the flow rate, and that's going up into the environment. Okay, it's going to come back down somewhere, rain, whatever. It's not being lost. It's just being lost from this particular site as we evaporate it. At the same time, as we're evaporating water, whatever's in that water is left behind. That concentration is going to build up in the water left behind because there's less water, but still the same amount of stuff. So we also have to blow down a certain amount of water to keep those concentrations from getting too high and causing damage or issues. And typically we'll blow down in the neighborhood of 1% of the flow rate also.
What do you mean by blow down?
Dump, get rid of.
Just dump it down the drain?
Yes.
Gotcha.
Or it's just to a waste treatment facility, kind of depends on the laws and codes and whatever's going on for that particular area. But yeah, you're getting it out of the system, out of the condenser loop.
Gotcha.
Yep. So we're extracting 1% to go somewhere else, and we're evaporating 1%. Point is, that's 2% of the flow rate that you're losing through evaporation and blowdown. For drift, we can get that down as low as 0.0005%. Typically, you'll see it around 0.001, at the most 0.005. So that compared to 2% is completely negligible. It's really not a water usage issue. What drift is and what it can be and what it does is it's little droplets that actually get entrained in the air and come out with the evaporated air, with the evaporated water. The evaporated water is pure water. I mean, it is pure vapor. But the little droplets that come out, those will have whatever's in the water in those droplets.
So hardness, chemical treatment.
Yeah.
Yep, everything in there.
That can cause damage. Probably the best example I can think of is, the BMW that sits outside the doctor's building at the hospital.
It's always the German cars outside.
It's always a doctor.
And it's no kidding. I mean, literally, you talk to anybody that's worked with cooling towers before in their life, it only happens to lawyers, judges, and physicians. I swear to you.
Yeah, so those little droplets get on cars and they don't look good, or they maybe start to damage the paint job. So that's the problem with drift.
And usually the drift rates that come from the manufacturer are, at least Marley does a pretty amazing job of testing for drift. So if you have drift on a newer cooling tower, usually it's an operational issue or problem. And so it's really important to go out there and take a look at it, because what can happen, what causes drift beyond this 0.005%, usually it's over pumping or an installation error. And so if you hear of a drift issue, you really need to get out there quickly and try to diagnose what the issue is. My opinion, and I'm kind of cutting this short because we're getting close to an hour. My opinion is there's really no significant advantage, and this could have almost been removed from the slide deck because it's kind of a moot topic. Anyway,
I would agree.
All right, okay. I gave you an old copy of the presentation, Ryan. So it's my fault that this is actually here. So can you scroll forward to the Advantage page? These are teasers. If we have a couple extra minutes, we'll talk about those.
Where am I getting to here?
Yeah, I think so.
Okay. Yeah. I think we've covered all the big hitters for sure. No doubt.
Right.
So.
Yeah. So. Yeah. I think what I'd like to do is just take the last few minutes that we have and talk more anecdotally about, when and why we would recommend one tower versus another tower, because that's usually when we get the best feedback from engineers when we do these presentations live, that's the best spot. So as we said it now, this will be the third time. Marley's awesome because they have every type of technology available in the cooling tower world. And, whether it's Counterflow, Crossflow, induced draft, forced draft, fiberglass, stainless steel, galvanized steel, they've done it all, and most of it's still available. And over my 30 years, I've probably recommended and supplied 10 to 1 Crossflow cooling towers versus Counterflow towers. And so people will ask me why, and they'll say, "Oh, it's just because Marley's historically a Crossflow cooling tower company," and which is not actually true. It's because the people that we work with are generally very concerned about the usability and the maintainability and the safety of the cooling tower. And so, if I think about some of our long-term customers, whether they be universities or manufacturing facilities or schools and school districts, they have robust maintenance people. Or did I just call the maintenance people fat? No, I didn't mean to. The people aren't fat, but the departments are big. Or actually they're shrinking because budgeting and financing. So it's important that they be able to take care of the equipment and do it safely. So for those reasons, the end users love using a Crossflow cooling tower. So then why do we recommend Counterflow towers? My experience is that because it's a square tower and in single cell configurations, the Counterflow tower can be more compact. I'll typically say the only time I recommend a Counterflow tower is when it's a very tight footprint that for some reason, as we make a selection, and with our selection software that we use, we could put in the parameters and say, pick a Counterflow and a Crossflow tower, whichever one's best. And so we're able to evaluate, the size and footprints and everything from a screen from a lot of cooling towers to pick from. So occasionally a Counterflow tower fits the site better than a Crossflow tower. So that's one reason I do it. The other reason is if first cost is the absolute only decision factor. Because, as we talked about before, those who want a Crossflow tower also typically want some nice things on it. It's kind of like when you buy a car, right? So if you're buying a car and you're going to have it for 2 years and it's only meant to get you to and from work 5 miles away, you might buy a very basic stripped down car. But if you're buying a family car that's going to be taking the kids back and forth to the grocery store, you're going to take a summer trip or two on it, you're going to want some amenities in it to make it a more comfortable, safer trip. As opposed to if it's just to get you back and forth to work, you might be in a very basic stripped down, 4-cylinder car. And that's kind of my opinion of Counterflow versus Crossflow towers. If all I need to do is cool 300 tons and I know I'm not going to maintain it, and I just need to get a tower on the roof as quickly and as inexpensively as possible, that might be when you look at a Counterflow tower. I don't know. Am I out of turn, Brian?
No, I would agree with that. I mean, if you look at the, I know our listeners can't see this table here, but there's a comparison of kind of all the things that are important to owners, operators, installers of cooling towers. And then we have kind of a matrix of Crossflow versus Counterflow. A lot of them are neutral. There's a couple of them where Counterflow wins out, but there's more where the Crossflow wins out. And in areas that are more important, like maintainability and efficiency and being able to operate year round, Crossflows have a significant advantage. So when you weigh it all together, you're almost always going to end up in a Crossflow, unless, like Troy said, there's there's a footprint constraint that you just can't fit a Crossflow, or some other special reason that's outside of the norm. So, yep. Don't think
there we go. I think we've heard an awkward pause there.
So does that mean the podcast is coming to an end with the awkward pause?
Yeah, I think.
Yeah, when you say "there we go," yep, that's kind of an indicator.
I run out of things to say.
Wasn't that our agreed cue for ending the show?
Okay, it is now. Yeah, Forrest Gump. That's about all I have to say about that. But actually, I think let's tease a couple of podcasts that will be coming up. We talked about installation considerations. I think that's one that we can do. And then one that I've gotten a lot of good feedback on, we called it, how to specify a cooling tower. And in parentheses, we would say no specky, no getty. So we'll have a conversation about proper sizing and specification of a cooling tower, because there are some specific things you want to be clear in your specifications to line out. Otherwise, you won't get them, and it can make a huge difference on the installation itself. They don't have to cost a lot, but it's a big difference maker. There you go.
I'd like to thank Troy and Ryan for being on the show. These episodes do take a lot of prep work and a lot of time to put together. So if you're listening, all I would ask as a thank you, just please give us 5 stars. You don't have to, a review would be even better. But if you at least just give us a thumbs up or a rating on your favorite podcast app, that helps the algorithm push us up closer to the top of the searches.
And subscribing,
yes.
If you've got topics you want us to talk about, we would love to do that. We are not a one-trick pony at Midwest Group, so we are a full systems supplier, and so we like to work on cooling towers, pumps, boilers, air handlers, chillers. So heat pumps, variable speed drives, all of the above. If it's a complicated applied type system, that's the stuff that we like to get tangled up in.
Where can listeners reach someone at Midwest Machinery?
Easiest way is just to go to midwestmachinery.net. .com will take you to a tractor supply place. .net will take you to our website. And we've got separate pages for our St. Louis, Oklahoma, and Kansas City branches, and I think a link to our Denver affiliate, Engineer Products.
Awesome. So again, welcome back for the season, all you listeners. Look forward to many more podcasts this year on many more topics. And until next time, keep engineering for tomorrow today.
Thanks for joining us on Engineering Tomorrow. If you liked the show, please take a moment to subscribe on iTunes or Spotify. For even more great engineering or construction knowledge, visit engineeringtomorrow.blog.